Okay, so then you should also do a recording. All right, great. Thanks everyone for coming. So today we had the pleasure of having Sharon, Ishu, and Lee here giving us a talk. So Sharon has a very impressive background. She graduated from Cornell, went to Stanford for a postdoc, then was at Facebook AI, and now finally a professor at University of Wisconsin-Madison. She has won many awards in the past, like 30 on 30 and Rising Stars, and so on and so forth. I'm sure you have a full trophy case. And she's worked on a lot of different things from fundamentals in deep learning to more recently the OOD distribution detection on deep neural networks. And today she's going to tell us about uncovering the unknowns of deep neural networks, challenges, and opportunities. Thanks, Sharon. Take it away.
Thank you, Greg, for the very kind introduction. Really excited to be here at the Physics Meets ML seminar. I would like to share some of the interesting challenges and opportunities on how to uncover the unknowns of deep neural networks. And during the talk, feel free to unmute yourself and ask questions. So I'd like to start the talk by showing you this video. This is a model trained on the Berkeley Deep Drive 100K dataset, performing bounding box tracking on the road. And needless to say, deep learning has achieved pretty remarkable success in many exciting areas like this. And I personally feel very fortunate to witness many breakthroughs. So today, instead of adding more praises, I would like to encourage you all to maybe take a step back and have a more critical look at the methods and technologies that we've built. And hopefully by the end of the talk, we can see things in a more well-rounded perspective. So I know there are many experts in statistics, machine learning, and physics in the crowd. So let's think maybe for a second how you would approach building and deploying such a self-driving car model. And so the typical process is to collect some training data with corresponding labels, and then train on your favorite machine learning model, say neural networks. And the output typically contains some predefined categories, in this case, pedestrian, car, and truck, and so on. And of course, there are thousands of other details to sort through. But let's say once you finally have a model with decent performance and you think it's ready to deploy on the road, more unexpected work has just begun. And why do I say that? Because the classic machine learning assumption is that the training and test data distributions match each other, right? So you would expect the car only runs around on the New York City street. That's what the model is trained on. However, in reality, these two data distributions can be wildly different, and this closed word assumption really holds true. And in this case, lots of unknowns could emerge. For example, we took this image from the MS COCO dataset, and it runs through the self-driving car model that we just trained on the BDD dataset. And so you can see that the model produced overconfident predictions for this unknown class, which is a cow, to be a pedestrian. And this was never exposed to the model during the training time. So in other words, deep neural networks, despite having remarkable performance on things that they were trained to predict on, but they do not necessarily know what they don't know. And this has raised significant reliability concerns because models, these algorithms that classify out of distribution samples into one of the known classes can be catastrophic. And so think about in healthcare, a medical machine learning model trained on a certain set of diseases may encounter a different disease, and it can cause mistreatment if not handled cautiously. And this issue is prevalent not just for high-stake domains, but also in many other scenarios where machine learning is being used. So imagine you're building an app of a food image classifier. And so the user can go to the grocery store and snap a photo. So to get some inspirations for what to cook for dinner. And for those of you who have worked with users' data of any kind or have seen what users' data look like, you would know how diverse and unpredictable it can be. And there could be a lot of images other than food. And so this is the precise of but essay data that I spent quite some time working with back in industry. And so my time working with real-world machine learning models has given me a firm belief on how important the following problem is. How can we build unknown aware deep learning models for reliable decision-making in an open world? And an important step towards this goal is to be able to identify and detect out of distribution data. And so what is out of distribution data, you might ask? Let me first provide a simple view on this. Let's say we have our training data distribution that is a mixture of two Gaussians for class label y equals to 1 and y equals to -1. And so our in distribution P of x in would be the marginal of the joint distribution that's defined over the input space x times the label space y. And these orange dots could emerge, which are out of distribution from an unknown class that doesn't belong to y equals to 1 or y equals to -1. So in other words, you don't want these orange dots to be predicted into either green or blue dots. And to translate this toy data into some high-dimensional images, you can think of cipher 10 as the in distribution on the left side, and SVHN, which the street view housing number, is the OOD, which have disjoint labels. Well, you might think that this OOD is way too obvious. I'm going to show you later how such an easy setup could trouble the state-of-art neural networks. And later on in this talk, I'll discuss how we can go beyond such simplified definition. And so let's stick with this simple view for now. And so SVHN is just one of the OOD that the model would encounter. And there are, of course, many other unknowns on this complex data manifold. If you think about all these possible images that the model could encounter on the internet. And so this is an image from a recent talk by Alec Redford from OpenAI, which I think nicely illustrates the complexity of the problem. And so out of distribution detection is a hard problem. And I would like to first explain the why before we attempt any solution to this problem. The first challenge is the lack of supervision from unknowns during the training time. And typically the model is trained only on the green and blue dots using the empirical risk minimization. And in this case, you can see these in distribution classes on the left side. And so you can't really anticipate where these orange dots would emerge a priori. And so that's the precise, the interesting and challenging part of OOD detection is you are trying to defend against something that you don't know where they could emerge from. And in particular, there's a huge space of uncertainty, especially in the high dimensional space. And the problem is further exacerbated by this high capacity neural networks that we're working with nowadays. And so if you look at the decision boundary at the bottom figure here, which tries to distinguish between the orange and the blue dots. These two are in distribution classes. And you see this middle decision boundary undesirably covers these red OOD data. So these red dots will be classified as orange with high confidence as well. Well, you might argue or ask, why don't we perform density estimation directly using deep generative models? And there are some unique challenges there to be solved too. For example, they can be difficult to optimize. And even if you can train it to converge, Eric Nalisnik in 2018 has this very interesting study that shows OOD data in some cases can actually cause high likelihood for a model trained on the ID data. And so at least for now, the performance of using deep generative model often lag behind the discriminative counterpart. And so for this talk, I'm going to stick with the latter approach, which is discriminative-based models. So over the years, there has been a lot of exciting progress made on OOD detection for deep neural networks. And I've highlighted a few in this slide, including some of our recent contributions in green. And in this talk, I'll try to unpack some of the ones that I'm particularly excited about. And so the earliest work adopted this post hoc approach for OOD detection. And so let me give you a method overview. A model is typically trained on the in distribution, in this case, say Cipher 10, using empirical risk minimization. And once the model is trained, let's take the network as it is without modifying its parameters. And so during inference time, for any given input, we're going to devise a scoring function S for OOD detection. And so essentially we're performing a thresholding comparison. If it's below a certain threshold, we're going to reject this input. And otherwise we produce the class prediction as usual. And so the advantage of this post hoc OOD detection is that it doesn't interfere with our original task. And so you can almost always guarantee the classification performance while having additional safety layer for free. And so an obvious baseline is to use the softmax confidence, which is defined to be the largest posterior probability at the bottom of the slide. However, it does not really work well because we saw some example earlier that neural networks can produce overconfident predictions for some of the OOD data. And so if you look at the distribution in terms of softmax confidence across many samples, and so here we plotted in purple the in distribution in gray of OOD data. And you see there is a high concentration. These two types of data, right, overlap a lot on these high confidence region as highlighted in this circle here. So it's non-trivial to draw a threshold somewhere to distinguish these two types of data. And so our early work on OOD was one of the first to address this issue by using temperature scaling and input preprocessing. And so the key insight there is that high temperature has a strong smoothing effect that would make softmax score distributions more separable between the ID and OOD data. And so in hindsight, what we realize, what OOD really is trying to do is to push the softmax score back to the logit space. And so we took this insight further. And in our NeurIPS paper last year, we proposed an energy-based OOD detection framework, which leverages the energy derived from the output of the neural network for detection. And so I'm going to spend some time diving into the details and explain how this framework actually works. So energy-based model was first introduced to the machine learning community in the 80s and has been around for decades. And to give you some quick background, an energy function takes an input X, say my cat, and corresponding label Y. And these two random variables would go through a function E of X comma Y and produce a scalar, which is the energy. And so this energy essentially measures this compatibility between these two variables. In this case, the picture and the corresponding label, and it should produce a lower value if it has high compatibility. And so this function can be non-probabilistic. If you want to turn it into a probability density, you can do so using the Gibbs distribution here. And so in this case, the posterior probability or the probability for the input to be associated with a label y is given in this form. And here this denominator, which is also known as the partition function, takes the integral over all the possible y's. And the free energy can be expressed as the negative of the log partition function, right? So far, nothing is new here. And so the question is, how is energy-based model related to neural networks in this context? And so it turns out a neural classifier can be interpreted from an energy-based perspective. And so let's consider a neural network producing these output logits, in this case, f1 of x, f2x, and so on. So notice this is the pre-softmax. And then after the softmax function, it would produce a normalized probability distribution, P of y conditioned on x. And this is the definition of softmax, which we have seen a couple of times in this talk so far. And so now if we define the energy function to be the negative of the logit output, this turns into something that we just saw earlier, right? And so recall, this is how free energy is defined. In the context of a neural network, the free energy replaces the integral with summation across k discrete labels, classes. And so now for every input x, and a pre-trained neural network parameterized by theta, this can be conveniently computed using the log sum exponential operation. And so in this work, one of the key ideas is to replace the softmax confidence score with energies for OOD detection. And so essentially, we're taking the same pre-trained neural network, but instead of calculating the softmax confidence, we're deriving the energy score. And so if you look at this distribution on the right side of this plot, you see that the distribution no longer have the spiky appearance that we saw earlier using softmax. And it's much smoother having this Gaussian-like distribution. And here to align with the convention, notice that on the x-axis, we use the negative. So we flip the sign to use negative energy, which is higher for in distribution and lower for OOD. And so during the inference time, we can apply this similar thresholding comparison. And if the negative energy is smaller than the threshold tau, it's classified as OOD, and vice versa. And to evaluate and compare our approach with the softmax confidence score, here we train a model on the Cypher 10 as in distribution. And we evaluated on SVHN as the out of distribution data. And so we measured this metric, which is called FPR 95, and this is how it's defined. So essentially, we look across the entire score distribution on the ID data, and we select this threshold so that 95% of the in distribution data is correctly classified or is above the threshold. And then we look at the fraction of OOD data, in this case SVHN, that's misclassified as in distribution. And so the lower FPR is going to be better. And so if we look at the softmax case, the FPR 95 in this case is 48.87. And in contrast, using energy score, improves the separability with a lower FPR score. And so we tested more thoroughly on a diverse collection of OOD data set and consistently observed a significant improvement. And so the blue bars are based on the softmax score, and the green bars are based on the energy score. And I do want to highlight that one advantage of using energy score is that it's very easy to compute, right? Using the standard log sum XP operation, and there's no hyperparameter tuning needed whatsoever, which was otherwise required for some of the previous baselines. And so I would also like to provide some explanation for why softmax score is suboptimal for OOD detection. And to explain this, let's first look at the training dynamics of neural networks in terms of how they change the energy state of the output. And so here is the standard cross entropy loss for classification. And so we're essentially taking the negative of the log probability corresponding to the ground truth. And so now we can derive the gradient of the loss with respect to all the parameters in this neural network, theta. You can skip the details, but what I want to highlight is that the training dynamics essentially tries to push down the energy for our training data distribution. And so E of X will be lower for in distribution. And so now if we look at the softmax score, or more precisely, the log of the softmax score, it can be decomposed into two terms. So here at the bottom, maybe you can focus on the bottom of the slide for now, highlighted in purple here. And so this log of softmax can be decomposed as the summation between the energy, which is the first term, and the maximum logit output, the second term. And recall that the first term will be lower for in distribution, and the second term is going to be higher for in distribution, because the neural network is trying to kind of push the maximum logit output to be as high as possible. So this overall summation results in a biased function that is no longer aligned, right, to reflect these OOD uncertainty. And so this explains why we have this biased distribution that's not very distinguishable when we use softmax. And so we can make the theory and analysis even more precise. And to do that, we have to make some assumptions, and analyzing the exact behavior of neural networks can be difficult due to this stochasticity of optimization and so on. And so in this work, we make this explicit assumption on this underlying data distribution, in this case, a mixture of multivariate and Gaussian. And so we assume that this mixture of Gaussian has equal priors for simplicity, which is 1 over k. And here k is the total number of classes, and with tight covariance matrix. And the simplicity is desirable because it allows us to precisely characterize the behavior of different OOD scoring functions, because now we have this ground truth, we have this explicit analytical form about the data density. And so here specifically, we can write out this class conditional density in this given form. So this probability of sampling an X given this class Y equals to I is in this form. And so based on this data distribution, we can write out the base optimal classifier. And this is just to plug in the standard class priors with the class conditional density. And so this posterior of Py equals to I conditioned on a given input is given in this form. And if we define this logit in this case to be the exponent of this Gaussian, class conditional Gaussian, and then plug in this energy definition that we saw earlier. And so we see that this energy score is proportional to the log of the data density with some scaling factor. And in contrast, we can also explicitly write out the maximum softmax score, which is essentially taking the max of P of y equals to I conditioned on X. And so everything can be derived explicitly, and we can see that the softmax score is in fact not aligned with the data density. And lastly, I thought this simple one-dimensional toy example is really straightforward to kind of see things. And so the gray line in the middle is the mixture of two Gaussian in this one-dimensional space. And the two means are centered around 2 and -2 respectively. And the top of the line, this blue line, is the maximum softmax probability. And so interestingly, you can see that at the two very end, which is highlighted in red, that's a region where the ground truth data density is in fact very low, right? So that's more likely to be an outlier region where you don't want this model to predict as in distribution. But the MSP function produces a high confidence, which is 1 in those cases. And in contrast, the bottom line in green is the negative energy. And so this is aligned with the data density. And so in practice, if you choose the threshold properly, despite some scaling factor, you will end up getting the same level set or OOD detection results. And we have a follow-up work this year that extends this energy-based framework to multi-label classification. And this is in collaboration with my previous intern, Sharon, who's now at CMU, and also Wei Tang and Alex. And to motivate the problem, previous studies have primarily focused on detecting OOD examples in the multi-class classification, where each sample is assigned to one and only one label. And this can be sometimes unrealistic or restrictive, where images can have multiple labels of interest. So for example, in the medical imaging case, there could be multiple abnormalities that are present in a single imaging scan. And so the main challenge in the multi-label classification setting is the need to estimate uncertainty that can jointly leverage information across different labels, as opposed to just rely on one single label. And in the case of multi-label, it's also difficult to attractively estimate the joint likelihood because it requires sampling combinatorially across many labels. And so the problem is actually harder than multi-class. And so how do we solve this, this problem? Well, we start by looking at the label-wise energy. And so in this multi-label classification setting, you can think of each label prediction is made independently by a binary classifier. And so this entire network will share the feature backbone up to this penultimate layer, and then split at the very end into k different binary classifier. And so here the logistic function or the probability for a particular class yi is given in this form. And if you look at this formula, this is actually a special case of softmax with just two logits, f sub yi, and also a constant logit output 0, which gives this one term 1 here in this denominator. And so now if we plug in the free energy definition that we saw earlier, which is the negative of the log of the denominator. This is what we define to be E of sub yi, the label-wise energy score. And so we can visualize and see the distribution of label-wise energy score. In this case, each of the row is an in-distribution class, which is from a subset of Pascal VOC data set. And this is highlighted in green. And the OOD data is selected from a subset of ImageNet classes that do not overlap with the in-distribution. And so there, you see that there's some nice separability here, but what's missing here is there's no way for us to jointly capture the uncertainty across different labels. And so we propose this scoring function called joint energy, which takes into account the joint uncertainty across different labels. And specifically, joint energy is defined to be the summation of label-wise energy across different labels. And so having multiple dominant labels is indicative of an in-distribution input, which is a characteristic that joint energy captures. And so you can see on the right side of this figure, when we use this summation, it creates a bigger gap in between this in-distribution and OOD, as opposed to relying on this dominant signal. And despite its simplicity, we can show that joint energy has some nice interpretation from the joint likelihood perspective. And I'm not going to the details here for the time being, but at the high level, we can decompose this joint energy into this combination of multiple terms in terms of joint conditional log likelihood and log of data density. And so both of these terms will be higher for in distribution, which is desirable for OOD detection. And this is a snippet of the performance comparison compared to the prior art. And we evaluated here on 3 different in-distribution data set. And all of them are multi-label classification, including MS-COCO, Pascal, VOC, and NUS-wide. And we show that joint energy has some promising performance here. And in the last part of the talk, I would like to spend some time maybe sharing some of the parting thoughts and on what would be the interesting opportunities moving forward for this field. And so the first opportunity is to identify the fundamental cause of overconfidence on OOD data. And so far, I have presented several work on the algorithmic solutions to OOD detection. But a question left in mystery is why neural networks produce overconfident output on these OOD data. And answering this question requires carefully examining the internal mechanism by which the network is trained and evaluated. And so in our paper this year, we provide some interesting insights on the potential costs and mitigation of this overconfidence issue. And this is joint work with my PhD student, Eo Sun and Chuan Guo from Facebook AI Research. And to explain the costs, I want to just quickly recap in case you're not familiar with this concept of batch normalization and how this affects the internal activations of neural networks. And so during training, batch norm is a commonly employed technique, which estimates the running mean and variance for each of the unit inside this neural network. And during inference, the network applies the batch norm statistics, which helps normalize the activation for the test data. An important thing to notice is that the batch norm statistics is all estimated based on the in-distribution data. And our key insight here is that using the mismatched batch norm statistics that are estimated on the ID data, but blindly applied to the OOD data, right? So these OOD data are not having similar appearance or statistics as the in-distribution data. And this will trigger abnormally high unit activations. And later I'll show you what it looks like. And also consequently model output. And so in other words, batch norm is actually both a blessing and a curse. It's a blessing for the classification, which helps stabilize the model training, but it's a curse for OOD detection. Because I will show you here, if we examine this activation pattern of neural network, and this is a model trained on the ImageNet, and I'm showing you this activation from the very end, the penultimate layer of the neural network. It's a ResNet trained on ImageNet. And each of the points in the x-axis corresponds to a single unit. And so there are a total 512 of them. And for each of the units, we show the mean, which is in this solid blue line. You can see roughly in the middle. And also the standard deviation, which are estimated on the entire training data, which is shown by this the shaded area. And then we can look at, on average, how these units respond to the OOD data. And keep in mind, these are the data that the network was never trained on, right? So these are completely new data that we're feeding into this network. And these images do not belong to any in-distribution category. And so here we show the statistics in gray here. Similarly, the mean is in this solid line, and the shade indicates the variance. And so if we contrast this activation patterns in between ID and OOD data, we can see that the activation for ID data in blue is well behaved with a near constant mean and standard deviation, right? So that's at the top of the figure. And in contrast, for OOD data in gray, this mean activation has significantly larger variations across units and is biased towards having sharp positive values. And it turns out such high unit activation can undesirably manifest in the model output and causing overconfidence on this OOD data. And I just saw a couple questions in the chat thread. I just realized, I think I'll come back to some of the early questions later on in this talk, but just quick clarification on this question of by overconfident, do you mean overfit? So by overconfident, we mean the output, which is the posterior probability or softmax confidence is abnormally high. So this is different from the concept of overfitting. And so this observation led to a very simple technique that we propose in this paper, which is called rectified activation, or in short, React, for OOD detection. And our key idea is to perform this post hoc truncation to the unit activation at a certain threshold. And so this is the threshold that we're applying here, right? And this can be done on a pre-trained model without modifying any of its hyperparameters or parameters. And this React operation is applied element-wise to all these unit activation. And a higher C indicates a larger threshold and vice versa. And so then you can derive the model output as usual. And during the test time, React can be leveraged by a variety of downstream OOD detection scores. And so this function could be, for example, the energy score that we saw earlier. And here is a preview of the performance. So this yellow bar is the energy score that I've described earlier. And the red is using React, is performing this rectified activation. And so that would prune out some of these abnormally high activations, which improves the OOD performance. And moving forward, I think there is the need to move beyond these post hoc OOD detection methods, which I have talked quite extensively about during this talk. But I don't think these post hoc methods are going to be sufficient to fundamentally mitigate the problem, because they don't change how the model is actually trained. And in particular, existing machine learning algorithms are primarily driven by optimizing the accuracy on the ID data. And so it's completely oblivious to what could happen outside the training data distribution, right? So the decision boundary can be very good for classification purpose, but they may be ill-fated for OOD detection. And so, for example, this middle plot here shows the decision boundary for three-way classification, and it does a perfect job just discriminating among these three classes. But this dark green area are high confidence regions that are not good for OOD detection. And what we ideally want is something that looks like the right side of this plot here. And so to achieve so, we need some training time regularization that not only optimize for the classification performance, but also account for some uncertainty that could take place outside the ID data, right? So the ideal decision boundary should be more or less aligned with the data density. And so one way to achieve this is using our proposed energy regularized learning. And so the training objective has two terms. The first one is the standard cross entropy loss. And in addition, we add this energy regularization. And what it's doing is to take care of this risk or uncertainty that could be outside from the in-distribution data. And so this regularization tries to shape this energy surface in the way that pull all this energy to be below this margin, this MN for in-distribution data. And so essentially we want energy to be as distinguishable as possible between two types of data, in-distribution versus OOD. And this can be achieved, for example, by using the hinge loss. And the result of the training is more separable distributions measured by the energy score, as you see on the rightmost side of this plot here. And in contrast, the left two plots are the post hoc methods, which are just taking the pre-trained model, applying softmax score or the energy score, and both are derived without applying any regularization during training time. And so we tested again on a diverse collection of OOD data. And here you can see the contrast of when we apply this regularization during the training time, the performance can be further improved as opposed to using the energy score or softmax score that we saw earlier. However, I do want to point out that utilizing this training time regularization do impose a stronger requirement because we do have to rely on this auxiliary outlier data during the training time. So to shape this energy surface explicitly. So that's one of the limitations that I do want to acknowledge here. And our work is also open sourced. Here is the GitHub link if you're interested in building further on our method. And I think moving forward, there are great opportunities for learning algorithm design. For example, as I mentioned, some of the methods would require using auxiliary outlier data, which may or may not always be feasible. And so we need algorithms that can impose much weaker or minimal data assumptions in this case. And we also need to design algorithms that can ideally learn a compact decision boundary between ID and OOD data as illustrated in this plot here. And so this would give us more accurate kind of estimation when data take place or is encountered during the test time. And so we have some recent exploration in this direction. If you're interested, please check out our paper. And lastly, I want to mention that there are also a lot of opportunities to think about how do we move beyond the simple benchmark and towards more realistic data model, right? And during the talk, I've shown you a lot of results based on the Cypher benchmark, but admittedly, there are some limitations. For example, these images are often have low resolution, 32 by 32, and the class space is also relatively small. They may not be reflective of the visual complexity observed in the real world. And so a natural question is there any way we can scale that beyond Cypher benchmark, for example, to ImageNet? Is that plausible? And so in the real world, images will often come from a larger semantic space with much, much higher resolution. And so we asked the question, is there any way we can do OOD detection for ImageNet trained model? And this is work I just want to briefly mention as we're reaching kind of the end of the talk. And this is a joint work with Ray, which was presented as CVPR earlier this year, that tries to scale OOD detection towards large semantic space. And so we started with this thought experiment just to see how well existing methods scale, right? As we increase the number of classes on the x-axis. And you see here the y-axis is the AROC, which is higher, is better. And interestingly, we noticed that as we add more classes to this in-distribution data set, the performance keeps decreasing. And intuitively, this is because the decision boundary between our training data and the OOD data becomes a lot more complex. And so the idea of this paper is to develop a group-based OOD detection framework that allows simplifying these decision boundaries. And so you can see the blue curves here are based on our method, MOS, which can effectively scale to a larger data set, all the way up to 1,000 classes. And as part of the paper, we also released a new benchmark based on ImageNet. And here is the link if you're interested in checking out and creating even better solutions. And let me quickly recap on what I have covered in this talk, and then afterwards I'll come back to some of the questions that are popping up in the chat thread. And so I started the talk by showing you some of the challenges and existing solution landscape. For example, methods that derive OOD scores from a pre-trained neural network, which we call post hoc detection using softmax confidence or using OOD score. And then I presented a recent energy-based framework that improves over softmax confidence. And it's also very easy to use and has some nice theoretical properties and guarantees. And then I also talk about several interesting opportunities. The first one is to actually understand, right? Aside from developing solutions, we need to understand what's really causing the overconfidence issue on these OOD data. And one of the plausible clue that we showed in recent work is from the Batching statistic perspective. And I also think there are enormous opportunities to develop learning algorithm to not only account or optimize for the classification performance, but also think beyond, have due objective that also optimize for the potential risk outside of the in-distribution data. And so this is can be achieved through, for example, energy regularized learning that add this regularization term to shape the energy surface in addition to the cross entropy loss. And lastly, I think there will be opportunities on the detection task design as well. And one of the direction is how do we scale beyond the simplified benchmarks such as CIFAR to something more plausible that's much closer to the data observed in the real world. For example, I think ImageNet is a good step towards this goal, but that's definitely not the end of, that's by no means the end of this direction. And so with that, I want to thank you for being here and listening to the talk. And I think I'll start addressing some of the questions that are popping up. I thought you guys would unmute and ask the questions, so sorry for not taking the questions earlier. Let me stop sharing the screen so we can see each other.
Let's first give a round of applause to Sharon's great informative talk.
Well, I see a lot of questions. Really sorry.
Yeah, there's quite a bit of questions. So I need to go in a couple of minutes. So let me ask some of my questions first.
Sure.
Like, do you have a idea, like in practice, what people do right now for out of distribution detection, like where money is involved? I don't know, Tesla, self-driving or something. I'm sure Facebook has some algorithm as well.
Yeah, that's an excellent question. So we do have some of the ongoing collaboration. I think right now the good news is that industry in general, right, is realizing the importance and the gravity of this problem and are looking more into plausible solution. And when we look at the industry world, right, one thing we have to kind of keep in mind is a lot of times for a model that's already being deployed and running inference on billions or millions of data, it can be disruptive if we try to kind of change the model. And so one of the solutions that I think industry likes better is the post hoc methods, right, without interfering with the existing model that's running. And that's why I spent quite some effort introducing this method, maximum softmax probability, energy score, and also React is also a very convenient post hoc method. And so I would say these are the great entryway for industry to kind of pick up on and start employing in practice. And moving forward, I think the ultimate nice situation would be actually during the training time, right? Factor in this possible outliers that could emerge to give even better solution.
All right. Do you have any comment on auto distribution for NLP?
That's another great question. So in my research, we have been looking quite extensively in the image classification domain and also object detection, and we haven't unfortunately done too much work in the NLP domain. But I know there are actually several interesting works coming out from the NLP community this year as well. So people are actively looking into that direction too. And I think some of the insights, right, what we developed in the image classification domain might be, translating. I mean, this to something to be verified, but I think there are opportunities to actually take some of the insights to the NLP task as well. Great question.
Right. Thanks. Great. So I need to go. Gary or Sven, can you take over for me, please?
Thank you, Greg. Nice to meet you.
Yeah, no,
nice
thanks so much for the talk. It was great. Okay,
Yeah,
so I'm gonna stop recording now and then I'm going to exit.
Yeah, thanks, Greg. I don't mind, Gary, but maybe we should move to the questions in the chat.
Sounds good. Sounds good.
Can you see them?
If David is around, he could ask.
Yeah, no, it's just a name question. You called it the Gibbs distribution, but I thought it'd be Boltzmann, or have I missed something that's important?
Yes, thanks for asking that clarification question. And I think, there is this inherent connection between, in neural networks, we often call the softmax function, right? That actually has this inherent connection to the Boltzmann distribution, which tries to establish the relationship between the energy state versus the probability. And so, we could actually, from a naming perspective, it's essentially the softmax can be viewed as both.
But also, am I right that your energy is like the log of the partition function with a minus sign?
Yes.
So that's the Helmholtz free energy, I think.
Yes, correct, exactly.
But then that leads to the next thing, that you can write that as the energy minus the temperature times the entropy. And so then there's also the idea that you're also weighting between the energy and a sort of intrinsic entropy of the system.
Are you referring to I think we use the notion of free energy, but if you actually subtract this entropy term, that becomes the total energy. Is that what you're referring to?
So I'm just saying that in what you have, where you've got F is equal to minus log Z, where Z is the partition function.
Correct.
That's the Helmholtz free energy.
Yes.
And then in physics, at least, that is equal to the energy minus the temperature times the entropy. So the Helmholtz free energy differs by the energy by the temperature times the entropy.
Times the entropy. I think we have done some of the early exploration, and empirically we did not observe a difference when we use the Helmholtz free energy versus when we factor in this entropy term.
Okay, yeah. I mean, it looks similar to what you were doing when you're adding in a regularization later of the energy, because then you're getting an additional piece with a lambda that looked like the temperature. So it looked like your regularization piece looked like a temperature going with the thing.
Actually, it's interesting you bring up this temperature. So that also plays a role there. And in the paper, I didn't go into the sublation for the talk, but if you're interested in the paper, we actually investigated, right, how this temperature actually affects the OOD detection performance. And so for the results that I presented, we set the temperature to be 1 without actually changing it. But you will see as we change, increasing the temperature or reducing it, the OOD detection performance would change as well. Yeah,
sure.
That's a great point.
Okay, thank you very much.
Thank you, David.
Okay, I think there is another question. Sanka Gilde, there's also a question I had as well. Is there an equivalent formulation for regression problems? So is there some way to talk about out of distribution if one is interested in a regression?
Yeah, that's another great question. So we don't have, so in the context of this work, we primarily focus on the classification setting, and we don't have conclusive results on the regression problem yet, but we recently started looking into, how we employ this energy-based framework for reinforcement learning. And that's actually closer to the regression problem. So maybe, hopefully I'll share more results as we develop further. That's definitely an interesting direction. Yeah.
So, and then there was a question again, what do these unit activation plots look like in the absence of batch normalization? So
I see. That's a great question. I wish I can have this plot to show you. I don't have that in front of me right now, but you can imagine without batch norm, the statistic would be more chaotic, right? Because essentially nothing is normalized. So you would see the magnitude in terms of the activation is also not normalized within this kind of the nice range that we observed. So it's much more chaotic.
So, okay. Sorry. Yeah, and I skipped somebody. So yeah, please unmute yourself and ask your question.
Oh, I think I see another follow-up question from Sang Hope, right?
Yeah,
how would...
Hi, it's me.
Oh, would you like to maybe just...
Sure. Well, thank you for answering 2 of my questions. I appreciate that. Yeah, in all the examples that you presented so far, you had, a clear difference between ID and OD samples during training. What if it's a mixture, just like real life data? How would you proceed then?
I love that question. This is something recently, I was actually reading a paper. This is something not my research, but I do want to share this interesting work came out from NeurIPS this year that actually considers the scenario where training data is a mixture of ID data and also OOD data, which they call open set label noise. And there's some interesting and surprising results that shows the OOD data actually plays some interesting regularization effect during this SPD optimization process. And I'm happy to actually share that work with you. It's not from my group, but I thought you might be interested in, taking a read into that direction. And in general, I think it's a good and reasonable problem formulation to consider that sort of allows us to break this assumption of training data is not perfect, right? It's not well curated to just contain in-distribution data. And in reality, you might encounter a lot more data. For example, in a weekly supervised setting, there will be data points coming from OOD setting as well. So
Gotcha. Yeah, it would be awesome if you could share that.
Absolutely.
Paper. Thank you.
Mm-hmm.
I have one more question, but I know there are other people, so I'll circle back, I guess.
Yeah, thank you for the questions. Do you mind putting your email address in the chat thread?
Sure, absolutely.
Thanks.
Another question from you.
Thank you.
If no one has another question, I have one more. I just don't want to step over anyone's questions. Yeah, my question is, have you considered the issue of with these post hoc calibration methods? Pardon me, post hoc, well, in a sense, calibration method. The calibration impact that it has on the actual ID predictions themselves. Like I know those histogram plots that you showed when you use energy as a metric instead of the softmax probabilities. The histograms get better separated, but what about the predicted, the calibration, the ACE or ECE or any other metrics?
That's an excellent question. So first, I want to kind of clarify, in terms of problem formulation, what calibration is trying to achieve is slightly different from what OOD, right? OOD is concerned about separating ID data from, something that's not trained on, versus calibration is completely focusing on the training data and try to make sure that the post area is representative of this true likelihood. And in this energy-based method that we showed, it actually does not interfere with the calibration, because we're completely deriving the score from the logit output space, and we're not changing how the confidence, which is post softmax, is defined. But I do want to point out a related work which I touched very briefly on, is precursor work called OOD. And so in there, they maybe let me share a screen here. And so this work has more connection to the calibration. So this one right here. So if you can see my slides here. So in this work, the scoring function is defined based on a confidence score that's after applying temperature scaling. And it's one of the useful technique for calibrating the model's confidence and probabilities. And so the connection here is that when your goal is to optimize for the calibration performance, and often you just want to apply some very mild temperature, let's say roughly empirically in between 1 or 2. And so that you can tune down these probabilities slightly for the in-distribution. However, we noticed that to get the optimal OOD performance, you actually need much larger temperature to bring this back to the logit space. And mathematically, I can show you this. This is all presented in the right here. So this is the connection I want to point out right here. So you can write out this confidence in terms of the unnormalized output at the bottom. So this is the confidence after Taylor expansion, where we only preserve the first order information and the second order. And you can see that when temperature is large enough, the confidence score is primarily, first of all, it's going to be smooth to, it's going to be closer to 1/n, and here n is the total number of classes. And as you can imagine, when you have a large class output space, say 1000, this confidence score is no longer probabilistic. And so that's not well calibrated, but it's optimal for OOD detection purposes, because there we don't really restrict this score to be, probabilistic in some sense. So I hope that clarification helps.
Oh, it does. Thank you.
Yeah, that's an excellent question. Thank you for raising that.
Right, and that's Liu, I think.
Yeah, just another question about the confidence.
Yeah.
So when you see overconfidence, like how can you tell when the model is overconfident? Like, is it related to overfitting?
Yeah, I think I try to address some of that confusion in the talk. And so when we say overconfidence, it could refer to two types of data. One is overconfidence to the training data distribution, and that's often when you want to better calibrate your model so that the prediction reflects the true accuracy, right, for this data to be predicted correctly. And so that's one thing. And the second concept is overconfidence to the OOD data. And that's what kind of what a lot of this talk and works are focusing on solving, is you don't want the model to predict anything with high confidence that was not trained on. Does that clarification help?
Yeah, so the latter is more like overfitting, I guess.
The latter, well, I would say it's not solely because of overfitting. It's more of models' lack of knowledge on what's outside the training data distribution. Because if you think about, model trained on Cypher10, the objective is solely trying to optimize for the accuracy on this, on this small region in this high dimensional space. And it's not explicitly accounting for what could happen outside. And so the model is essentially oblivious to this OOD space, right? And so it's not just overfitting, I would say. And it's a lack of regularization. on you know what could be, you know, what the model should react for a region outside the in-distribution data.
Okay, thank you.
Then
I
there's
have a question.
Yes, exactly.
My questions are about transfer learning. So you train the model, especially incorporates the energy regularization. This would hurt the transfer learning. Let's say I train a model for one domain, I want to transfer to the different domain. Also, the situation is I want to increase the number of the classes. So does this also hurt the incremental learning?
That's an excellent question. I haven't thought about this. And so it might, because, you know, it depends on your goal, right? If you set this in-distribution domain to be, we apply this regulation essentially tries to reduce the decision boundary to, you know, to be around in-distribution as tightly as possible. And as you said, that may inevitably affect the transferability, right? Because you're restricting the knowledge and feature to be just solely focusing on that in distribution. I don't have a good answer, to be honest. I think that's something perhaps worth a further study and future exploration. Excellent question.
Thank you.
Yeah, thank you for raising that. Very interesting.
Yeah, thank you.
Thank you for thinking more.
All right. I think that's all the questions in the chat and that have been raised. So I think we can thank you again for a very nice talk.
Thank you everyone for hosting me, for inviting, and all those excellent questions. And if you have any more questions, feel free to follow up through email. Thank you so much.
Thanks, Sharon. Hope to see you soon.